We were looking last time at problems of 2 and 3 dimensional unsteady state heat conduction. Before that, we had looked at 1 dimensional unsteady state processes in an infinite cylinder, for which I had given you a solution, a series solution and a solution in the form of charts and how to use them. And then I had mentioned that the same type of solution is available for a long solid cylinder as well as for a solid sphere. And then we had started discussing 2 and 3 dimensional unsteady state heat conduction. And I said, suppose we have a long rectangular bar like this and of dimensions 2a and 2b, and initially this bar is at a temperature, initially it is at a temperature T 0, it is immersed at time t equal to 0 in surroundings at a temperature T f. There is a surface heat transfer coefficient on all faces h. Then obviously, the temperature is going to be a function of x, y and time. We would like to solve for this temperature distribution. So, we will formulate the problem like we did for the 1 dimensional unsteady state. Let us formulate the problem. That means, let us put down the differential equation, the boundary conditions and the initial condition for this problem. First of all, the differential equation for this problem, go back to the general differential equation and take t as a function of x, y and time, eliminate the heat generation term, take k equal to constant, and you will get the differential equation straight away as d 2 theta dx squared plus d 2 theta dy squared is equal to 1 upon alpha dt dt. That is the differential equation you will get, d theta dt, sorry, not dt dt, d theta dt. All right. Now, I am putting the differential equation straight away in terms of theta, because I am defining theta in the same way, theta is equal to T minus T f, like we did earlier, T f being the surrounding temperature. Okay. So, what is the initial condition? We have to solve this differential equation subject to the initial condition at time t equal to 0, t is equal to t 0 or theta is equal to t 0 minus t f, which is nothing but theta 0. And the boundary conditions will be as follows. Now, while putting down boundary conditions, let us make use of the symmetry of the problem. That means, let me go back to the sketch which I had of the bar. We have a choice. We can either put down boundary conditions at x equal to a, y equal to x equal to minus a, y equal to b, y equal to minus b, or recognizing that there is symmetry in this problem, we say let us solve the problem only in the positive quadrant, in which case we will put down the boundary conditions at x equal to a, x equal to 0, y equal to b and y equal to 0. That is what we will do. Right? If you recognize symmetry, you need to solve only in the positive quadrant. So, we will put down boundary conditions at the 4 edges of this positive quadrant. And what will they be? The boundary conditions would be at x equal to 0, d theta dx at x equal to 0 has to be 0, symmetry requires that. D theta dy at y equal to 0 also must be equal to 0, symmetry requires that. And then at the two faces, x equal to a we will get minus k d theta dx at x is equal to a is equal to h times theta at x is equal to a, and at y equal to b we will get minus k d theta dy at y equal to b is equal to h into theta at y is equal to b. All right. This is the full formulation of the problem. The differential equation, the initial condition and the boundary conditions in the positive quadrant, making use of symmetry at x equal to 0 and y equal to 0. Now, this problem has been solved also. This differential equation subject to this initial condition and the given boundary conditions has also been solved, and the solution very neatly enough comes out to be of the following form. Now, we are not solving the problem ourselves. I am just going to give you the solution which has been obtained. The solution which has been obtained is as follows. It has been shown that the solution to the problem is given by theta by theta naught, the same way that we had for the one dimensional situation, is equal to theta by theta naught x multiplied by theta naught y. This is what we call as a product solution, a product type solution. And the quantities theta by theta naught x mean theta by theta naught with the subscript x stands for, it is the solution, theta by theta naught x is the solution for the dimensionless temperature in an infinite slab of width 2a. That is what it is, which we have already with us. This solution we have from the infinite slab solution, and theta by theta 0 y is the same thing, is the same solution, is the solution for the dimensionless temperature in an infinite slab of width 2b. So, do you understand? For a rectangular bar, all you have to do is to treat it as if you have got two infinite slabs, one of width 2a, one of width 2b. Obtain the solution theta by theta 0 x for a slab of width 2a, obtain the solution theta by theta 0 y for an infinite slab of width 2b, multiply the two to get theta by theta naught for the rectangular bar 2a by 2b. That is all you have to do. So, it is a very, very neat solution which has been obtained. And as you know, theta by theta 0 x and theta by theta 0 y will come, these values will come from the charts which we had earlier, all right, or from the series solution for the one dimensional case which I have given you earlier. Now, the same idea can also be extended to a three dimensional situation. The three dimensional situation is the following. Suppose I have a rectangular block, let us say I have a rectangular brick or a rectangular block of dimensions 2a by 2b by 2c, a rectangular brick or a block of this size. It is initially at a uniform temperature T naught. I put it in surroundings at a temperature T f. The heat transfer coefficient on all the 6 faces of this block is h. Find the temperature at any point in this block as a function of time. Okay. Now, T is going to be a function of x, y, z and time. And interestingly enough, in the same way, in a similar way, in a similar way. The solution has been obtained, for this case has been obtained to be theta by theta naught is equal to theta by theta naught x multiplied by theta naught y multiplied by theta naught z, where the three quantities on the right hand side, theta by theta 0 x, theta by theta 0 y, theta by theta 0 z, are the solutions for infinite slabs of width 2a, 2b and 2c, which we can obtain from the series solution I have given you earlier. So, it is a very straightforward job to use these product solutions for one for the rectangular bar, a long rectangular bar, and secondly for a rectangular block of 2a by 2b by 2c. All right, now we have come to the end of what we wanted to do with unsteady state conduction. We have done one dimensional unsteady state in an infinite slab, we have done one dimensional unsteady state in an infinite solid cylinder. We have also done something for a, I have also indicated that a similar solution has been obtained for a sphere, and I have indicated how these solutions can be applied to problems and can be extended to 2 and 3 dimensional unsteady state problems for a rectangular bar, a long rectangular bar as well as for a rectangular brick. Now, we want to go on to a new topic, and that new topic is the topic of fins or extended surfaces. The first thing we want to ask ourselves is, when are fins used? We want to go to the topic of fins or extended surfaces. Fins are used to reduce the thermal resistance at a surface and thereby increase the heat transfer rate from the surface to the adjacent fluid. That is when we use fins, or as we call them, extended surfaces. I repeat, fins are used to reduce the thermal resistance at a surface and thereby increase the heat transfer rate from the surface to the adjacent fluid. Now, what is the heat transfer rate given by? Heat transfer rate Q for any given surface is given by the thermal temperature difference between the wall and the fluid, or the fluid and the wall, delta T, divided by the thermal resistance. And if there is a heat transfer coefficient H at the surface and the area of the surface is A, then we would say it is delta T divided by 1 upon H A. All right. Delta T is the difference of temperature between the wall and the surrounding fluid. So, Q is given by this. Now, suppose for a given situation, this thermal resistance 1 upon H A, this thermal resistance 1 upon H A is too high. I want to lower it in order to increase Q. I can't change delta T. I want to lower 1 upon H A, the thermal resistance, in order to get a higher value of Q. Introduction of fins or extended surfaces helps me in lowering this value of the thermal resistance. Okay. Now, let us look at some geometries that are used. Let me show you some instances of fins being used. Here is a figure. This is a plane surface, area A, okay. H is the heat transfer coefficient, Tf is the fluid temperature over it. We get a certain heat transfer rate from this surface. I want to increase that heat transfer rate. So, what do? I put fins on this surface. The fins in this case, as shown, are nothing but thin plates which are stuck on the surface, all right, at right angles to the surface. The fins are height L, width B and thickness T. Usually thin plates side by side would be stuck, and they would help to reduce the thermal resistance. Or the fins could be in the form of just rods sticking out of the surface. These would, if they are thin rods, thin relative to the length L, they would be like pins. So, we call them as pin fins typically, all right. They could be square in cross section, they could be circular in cross section, they could have any cross section that we like. But the point is, we are adding some surface area on the main base area, which is the horizontal part here. And the addition of this area through the use of extended surfaces helps to reduce the thermal resistance. That is the main point about fins or extended surfaces. Let us look at some more examples. I now go to the case of a cylinder. Let us say this is a hollow cylinder. It could be, say, the cylinder block of an engine, an internal combustion engine, losing heat to the surroundings. In order to reduce the thermal resistance at the outer surface and therefore increase the heat transfer rate, we put circumferential fins, and the ones that are shown here are circumferential fins with a rectangular cross section around this cylinder. In B here, these are also circumferential fins around the cylinder, but they are circumferential fins with a triangular cross section. We could have a variety of cross sections. I am just showing two as an example. Typically, we use circumferential fins with rectangular cross sections or with a slight taper or with triangular cross sections. All right, these are typically used, and as I said, the purpose is again the same as for the plane surface, the idea being to reduce the thermal resistance on the outer surface. Now, what we are going to do in this class is the following. We are going to look at one particular fin, namely the pin fin. We are going to analyze it in some detail. What is a pin fin? A pin fin is nothing but a rod sticking out of a plane surface. One could have a series of them. Let us analyze one. What we do for one is valid for all. So, a pin fin is nothing but a rod sticking out of a plane surface, and we use the word pin to signify that it is a slender rod. That is why you use the word pin. And the moment it is slender, what follows is that we do not have to worry about the temperature variation across the cross section of that pin fin. What we need to worry about is only the temperature distribution along the length L of the pin fin. You follow? That is the idea. A pin fin is a slender fin. Because of its slenderness, there is negligible variation of temperature across the cross section. The only worthwhile variation, which is worth analyzing, is the variation along the length L. So, let us look at such a pin fin. This is a pin fin here now. In the previous sketch, I had shown it vertical, now I am showing it horizontal, that is the only difference. Here is the base surface, which I have hatched here, and the pin fin is of length L. I have drawn some arbitrary cross section and said, assume that the perimeter of the pin fin is P and its cross sectional area is A. It could be circular, it could be square, it could be a rectangular cross section, it does not matter. The point is, it is a slender cross section compared to the length L, that is the point. Okay. Now, I have already said that the moment, because it is slender, variations of temperature along the cross section are negligible, like this, they are negligible. Therefore, temperature will vary only in the x direction, the x direction being the direction along the length. And since we are dealing with a steady state situation, temperature will therefore only be a function of x. For such a pin fin, let us say the temperature at the base is T1. Let us say the temperature at the base is T1. Now, you know very well, if the surrounding temperature is Tf and T1 is greater than Tf, then it follows that along the fin, as you move along the length outwards away from the base plate, base surface, the temperature is going to drop and is gradually going to approach the value of Tf as we go further and further away. All right, that is what we are going to see. We want to solve for this temperature distribution. We want, this is a function of x, we would like to get T as a function of x. We will like to solve for it, and once we have solved for it, we will be able to calculate the rate at which heat flows from the surface of this fin. All right. So, our objective with this simplification, that is a pin fin, Therefore, T is only a function of x. Our objective is to find the temperature distribution along the length, that is T as a function of x, and to find the heat transfer rate from the surface of the fin all along its surface. That is our objective. Okay. What we will do is the following. We will say, consider, in order to derive the differential equation for this case, we will say consider a closed system like this, shown shaded by me here. That means, at a distance x take a cross section, at a distance x plus dx take a cross section, you will cut out an elementary volume of width dx and cross section equal to the cross section A of the fin, A times dx. You will cut out an elementary slice A times dx. Consider the heat balance on this elementary slice of width dx. What do we get? Let us look at that now. Let us write that down. Let us apply the first law of thermodynamics to A times dx. Apply first law of thermodynamics to the slice A times dx. Okay. Now, let me go back to the sketch here again for a moment. Notice I have drawn 3 arrows here. Qx, which I am showing here, is the rate at which heat is being conducted into the element by heat conduction, that is Qx. Qx plus dx is the rate at which heat is being conducted out of the element by heat conduction, and we also need to consider the heat flowing by convection from the surface of the slice, and that is H, the heat transfer coefficient, into the surface area P times dx, where P is the perimeter, into the temperature difference T minus Tf. So, this is the heat being lost by convection from the surface of the elementary slice. So, what do we have now? Let us put down expressions for these quantities. The first law says Qx is the heat flowing in by conduction, that must be equal to the heat flowing out by conduction plus the heat being lost by convection from the surface, and that is H P dx, which is the area, into T minus Tf. That is the convective heat loss from the surface. Now, from Fourier's law, Qx is nothing but minus K A dt dx, and that is equal to Qx plus dx is minus K A dt dx. If I move a distance dx in the positive x direction, I will get d2t dx squared multiplied by the distance I move dx, that is the increment on dt dx, plus h p dx t minus df. Okay. And on simplification, you can see the dt dx term is going to cancel, this is going to cancel with this. So, on simplification I will get d2t dx squared minus hp by ka is equal into t minus tf is equal to 0. That is the differential equation I am going to get for this case. As usual, I will again define theta as being the excess temperature above the ambient temperature, theta equal to T minus Tf. Let us define that, and if we do that, we will get, on simplification, we are going to get the differential equation in terms of theta as, we get the differential equation in terms of theta as d2 theta dx squared minus hp by ka theta equal to 0. That is our differential equation. It is a second order linear differential equation, very simple to solve. What are the boundary conditions under which we will solve it? We will need two boundary conditions. So, the two boundary conditions would be one at x equal to 0, one at x equal to L. At x equal to 0, t is equal to t 1. So, theta is equal to theta 1, straightforward. At x equal to L, we have a variety of boundary conditions to choose from, but let us choose a boundary condition which is usually adopted, and that is the following. We will say, I have already said the pin fin is fairly slender and long relative to its cross sectional dimensions. Therefore, by the time you reach almost the fin tip, the heat flowing out at the edge, right here, which I am showing again, I am showing the sketch of the fin again, the heat flowing out at the edge right here from this face, this is likely to be extremely small, what I have shown by the red arrow just now. And if it is small, let me assume that it is 0. If it is 0, it follows from Fourier's law of heat conduction that the d theta dx at x equal to L must be equal to 0. So, we make the reasonable assumption that the heat loss from the fin tip is negligible, and therefore, at x equal to L, we will take d theta dx equal to 0. Okay. So, that is our second boundary condition that we will take. Solve this differential equation subject to these two boundary conditions. As I said, it is a very simple differential equation. The general solution of this differential equation is equal to theta is equal to C 1 e to the power of m x plus C 2 e to the power of m x minus m x, which all of you should know, where m is equal to square root of h p by k a. Okay. It is a straightforward solution. Now, use the two boundary conditions to get the values of C 1 and C 2, and if you do that, we will get the solution to the problem to be, for the temperature distribution, we will get the following temperature distribution. We get theta by theta 1, instead of putting the solution in the form e to the power m x and e to the power minus m x, we will use the hyperbolic cosine and we will get theta by theta 1 is equal to the hyperbolic cosine m L minus x divided by the hyperbolic cosine m L. That is what we will get for the temperature distribution. It is a very simple solution that we get, because it is a very simple differential equation, where as defined earlier m is nothing but the square root of h p by k a. So, this is the temperature distribution, the equation that we have got for the temperature distribution, which I sketched for you earlier. Once we have got the temperature distribution, we can solve for the rate of heat flow from the fin surface. That is what we are interested in, the second thing we are interested in. What is the rate of heat flow from the fin surface? That we will call as Q, so many watts. What will it be? If I go back to the fin again for a moment, let me show the fin again. We want the rate at which heat is flowing out through the fin surface, like this, all over to the surroundings. All this heat must have originated at this point. It has to come from the base surface here at x equal to 0, enter the fin and then go out. You understand? So, all the heat that is flowing out must ultimately have originated here and then flows out like this. So, we can also say the heat flowing out all over the surface is nothing but, by Fourier's law, is nothing but minus k d theta dx at x equal to 0, that is at this cross section. So, let us put that in. We will say rate of heat flow from the fin surface is nothing but minus k a d theta dx at x equal to 0. And if you use the temperature distribution equation which I gave you, find out d theta dx from it, put x equal to 0, which is a line or two of calculation for you to do. You can show that this will come out to be the square root of h p k a multiplied by theta 1 multiplied by the hyperbolic tangent m L. So, that is the rate of heat flow from this fin surface. So, we have got the answers to the two things we are looking for. We have got an equation for the temperature distribution in the pin fin, we have an equation for the rate of heat flow Q from the fin surface, so many watts, the rate at which heat is flowing. Now, with fins, it is usual to define a term called the fin effectiveness. For all fins, not just pin fins, for all fins, it is usual to define a term called as the fin effectiveness, which we will denote by the symbol phi. And it is defined as follows. We say the fin effectiveness phi is equal to the actual heat flow rate Q from the fin surface divided by the Q you would get if the thermal conductivity of the fin material is infinity. Q upon Q which would be obtained if the thermal conductivity of the fin material is infinite. Mind you, suppose the thermal conductivity of the fin material is infinite, then again to go back to the sketch of the fin here, what would be the temperature distribution? If the thermal conductivity of this fin is infinite, then T is equal to T 1 at the base, then an infinite thermal conductivity requires that T is equal to T 1 everywhere along the fin length. There will be no drop in temperature like I am showing here, you will get T equal to T 1 everywhere. So, K equal to infinity means a temperature distribution T equal to T 1 everywhere along the length of the fin. Okay. So, this is how we define a term called as fin effectiveness. For a pin fin, what will we get? For a pin fin, phi is equal to, the fin effectiveness is equal to, in the numerator I put square root of H P K theta 1 hyperbolic tangent of m L, which is nothing but this expression, all right. In the denominator, recognizing that the temperature is T equal to T 1 along the whole length, if the temperature is T equal to T 1, the temperature difference with the surroundings will be T 1 minus T f all along the length, that means theta 1, and therefore, the rate at which heat is lost will be H into P L, which is the surface area of the fin, P is the perimeter, L is the length, into theta 1, which is the temperature difference T 1 minus T f. So, H P L theta 1 is the heat that would be lost from the fin surface if the conductivity of the fin material is infinite. If you simplify this whole expression, you will get hyperbolic tangent m L upon m L. So, that is the expression for the fin effectiveness of a pin fin, all right. Okay. Now, how do we use? Let me just show you a graph in which I have plotted the effectiveness of a pin fin. The same equation that I showed you, phi equal to hyperbolic tangent m L upon m L is plotted here. This is phi and this is m L, just writing it in big letters again. We are plotting that equation, hyperbolic tangent m L divided by m L here. Effectiveness, this is the effectiveness of a pin fin with a constant cross section. Okay. Phi plotted against m L. How do we use this solution now? We use it as follows. We say, we suppose I have a pin fin of a given length and a given cross section and certain given conditions. For that pin fin, you can calculate m L. The moment you get m L, go to this graph here, for that value of m L go up, then go horizontally and get the value of phi for the pin fin. So, for a given fin, calculate m L, go up, intersect this graph and then go horizontally till you get the corresponding value of phi. Once you have got the value of phi, multiply by q, when you, the value of q you would get if k is equal to infinity, and you will get the actual heat transfer rate from the given pin fin. So, for a given pin fin, proceed first for a given value of m L upwards, then horizontally to get a value of phi. You may have to do the reverse problem. The reverse problem is find the length of a fin required to achieve a certain heat transfer rate q, in which case you would go in the reverse direction. You would know a value of phi, you would go horizontally and then you would come down in order to find a value of m L. All right. Try doing both types of problems yourself. I would like you to do both types of problems. I will do one type, I would want you to do the other type yourself. So, let me illustrate now this whole idea. Let us take a problem. We will say, let us do a problem now of a pin fin. I am going to take up the following problem. Let us say on a surface, certain base surface, I have 50 pin fins, 50 pin fins. Each pin fin 1 centimeter diameter, 10 centimeters long. I am just taking some dimensions, simple dimensions. Circular pin fins 1 centimeter diameter, 10 centimeters long, attached to a wall. Fins are made of copper. Fins are made of copper, K equal to 300 watts per meter Kelvin, high value of K because it is a metal and that too a fairly pure metal. Value of H at the surface given to be 15 watts per meter squared Kelvin. Calculate Q for the fins if the temperature at the base T1 is equal to 200 centigrade and the surrounding temperature Tf is equal to 30 degrees centigrade. This is just a straightforward substitution into what we have done. All right. So, let us do that. Calculate Q for these 50 pin fins. Let us substitute the numbers now. First, let us get ml. ml in this case, ml is equal to square root of Hp by Ka to the power of half multiplied by L. So, that is equal to H is 15, P is pi into 0.01 divided by K is 300, A is the cross sectional area which is pi into 0.005 squared, pi r squared. Take the square root of this and multiply it by the length L which is 0.1 in meters. This comes out to be 0.447. So, the effectiveness phi is equal to the hyperbolic tangent ml divided by ml, which comes out to be, if you calculate it, 0.938. Therefore, Q is equal to 50, the number of fins, into the heat transfer rate from one fin, which will be pi into 0.01 into the length pi dl. This is the surface area of one fin, into the heat transfer coefficient 15 multiplied by the temperature difference 200 minus 30, all right, pi d L into 15 into 200 minus 30. This would be the heat transfer rate if K is equal to infinity. If I multiply this by the fin effectiveness, I get the actual heat transfer rate. So, this comes out to be 50 into 7.514, which is equal to 375.7 watts. So, that is the answer. It is a straightforward substitution problem. Given 50 pin fins with certain data, find the value of Q which you would get for a given values of the temperature and the surrounding temperature and the temperature at the base. Now, we want to look at another problem. The problem which we want to consider next is the following. Consider that I have, we are now doing one more problem of a pin fin. Suppose I have a rod which is 1 centimeter in diameter. Consider a rod 1 centimeter diameter, 20 centimeters long, all right, which is fixed between two walls, each of which is at a temperature of 200 degrees centigrade. This is the situation I am visualizing now. These are two walls, all right, between which I have a rod stuck, thin rod, 1 centimeter in diameter, 20 centimeters long. Okay. This is 20 centimeters long. And it is stuck, it is fixed between two walls, and the walls are at temperature, both of them are at temperature of 200 degrees centigrade. We are told that the K, the thermal conductivity K of the material of the rod is 300, so many watts per meter Kelvin. The heat transfer coefficient at the surface is 15, H is 15 watts per meter squared Kelvin, and the surrounding temperature Tf is 30 degrees centigrade. Tf equal to 30 degrees centigrade. All right. It is a rod fixed between two walls at 200, surrounding temperature is 30 degrees centigrade, H is 15, K of the rod material is 300 watts per centimeter Kelvin, watts per meter Kelvin. Now, what kind of temperature distribution will you get in this rod? If you were to sketch it, I think you will agree with me that you have got a symmetrical situation. So, you are going to get some kind of a temperature distribution which is going to be like this, going to go down, and then it is going to go up. That is the kind of temperature distribution you are going to get in this rod. All right. The line drawn in red, temperature is going to go down and then going to go up again to 200. Starts at 200, goes down and then goes up. And at the center, that is as x equal to 10, at the center here, symmetry requires, at the center obviously, since everything is symmetrical on both sides, symmetry requires that d theta or dt dx be equal to 0. All right. So, once you recognize that this situation is one in which there is symmetry, what you have in effect, the situation that you have with this rod is in effect equivalent to two pin fins which are attached to each other. I would like to find out, by the way, I should say that what are we looking for? We want to know what is the heat transfer rate from this rod. Okay. So, recognize now straight away that in this case the situation is equivalent. Situation is equivalent to two pin fins attached to each other. At x equal to L. That is what we have got. And therefore, if I ask now what is the Q for this, you will say straight away the Q for this situation is equal to 2 multiplied by the heat transfer rate from one pin fin 10 centimeters long, and that is nothing but 2 times 7.514, that is the answer of the previous problem because the data is identical, and that is equal to 15.028 watts. So, the case of the thin rod in this case is equivalent to 2 pin fins, that is what we are really saying. Now, we have analyzed only the pin fin here, but keep in mind that there are solutions for a variety of pin fin configurations available in the literature, and in every case, almost in every case, after obtaining the temperature distribution, the solution finally is in the form of a fin effectiveness plotted against some geometric parameter of the fin. For instance, you recall when I started talking of pin fins, I referred to circumferential fins with rectangular cross section. You recall I showed this geometry and I said around cylinders we put circumferential fins like this. Now, for this case, this is a well analyzed case of a circumferential fin around a circular cylinder. For this case, the fin effectiveness phi, let me write this in bigger letters, the fin effectiveness phi is plotted against a parameter L square root of h divided by k y b, where y b is half the width of half the thickness of the circumferential fin. All right. This is a chart which is available in almost all the standard books, it is not something new, but keep in mind this is very similar to the chart which we got for the pin fin. And how would we use it? In the same way, given a certain circumferential fin with given dimensions x e, x b, y b, etc. Go to this chart, calculate the x axis parameter L into the square root of h upon k y b. Then from this, for the given value of x c by x b, go up vertically to the given value of x c by x b, go horizontally, get the value of phi, multiply this phi by the heat transfer rate you would get from the circumferential fin if it has an infinite thermal conductivity. So, in exactly the same way as a pin fin, you would use this chart in order to find the heat transfer rate from circumferential fins with rectangular cross sections. Such solutions are available for a variety of fin shapes. We have done here in the class only the pin fin, and I have shown you the chart for fins with rectangular cross section, but keep in mind such charts or equations are available for a variety of fin shapes. Now, we have come to the end of what we wanted to do in heat conduction, and let me just sum up what we did quickly. Let us sum up what we have done in heat conduction. First of all, we started with one dimensional steady state situations, one dimensional steady state situations. All right, and we looked at the infinite slab, we looked at the infinitely long hollow cylinder, got simple solutions for temperature distribution and heat flow rate for these cases. I told you how to solve on your own to solve the problem for a hollow sphere. Then we introduced the concept of a thermal resistance. and we got expressions for the thermal resistance again of an infinite composite slab and an infinitely long composite hollow cylinder. All right. And our reason for introducing the concept of a thermal resistance was thermal resistances in series are additive like electrical resistances in series. And then following in this basis, we looked or we introduced the idea of a critical radius of insulation for a pipe, saying that there are situations in which if the outer radius R 2 of a pipe is below a certain value, then the addition of insulation may not help until we have put a certain minimum thickness. We got an expression for the critical radius of insulation. Then, in order to extend ideas to more general situations, we derived the general differential equation. We derived the general differential equation both in Cartesian coordinates and in cylindrical coordinates Using this general approach, we solved some problems of heat generation. Some one dimensional problems, 1D problems of heat generation in a slab as well as in a cylinder. Then we looked at unsteady state. Unsteady state heat conduction, and in this, first of all we said, suppose we neglect internal temperature gradients, negligible internal temperature gradients, then we have a situation in which T is only a function of time, a very simple situation which can be solved regardless of the shape of the object. But the moment you cannot neglect internal temperature gradients, then we have more complicated situations, internal temperature gradients not negligible, and for this case we looked at the infinite slab. I set up the problem, indicated how the solution is available in the form of charts. Then we also indicated how the solution is available in the form of an infinite solid cylinder and a solid sphere. Then we look today at 2D and 3D problems, rectangular bar and a rectangular block, and indicated how a product type solution is available for them. And finally, we have looked at fins, and in particular we have looked in detail at the pin fin, derived an expression for the temperature distribution in the pin fin and the effectiveness of a pin fin. I have also indicated that there are charts available for the effectiveness of so many other geometries of fins. So, we have come to the end of what we want to do with conduction. Next time, we will start with thermal radiation.